Okay, we'd like to thank Dr. Hennigan and the class for allowing us to be here. We've all been studying Mars for the last several weeks, and before that, we love it. We know there's some challenges that have to be overcome, so we've been reading some of the literature, we've been listening to Elon Musk's interviews, they're awesome. And we know that you guys have some concerns. There's not as much solar energy, it's far away, there's not as much wind. But we want to show you today how we think we can overcome some of those things and establish a colony. But first, we want to show you our idea of what the Martian should be.
I guarantee you that at some point, everything's going to go south on you.
Really?
You're going to say, this is it. This is how I end.
So as you can see from our video, we kind of hinted at the different energy sources that we think are applicable to Mars. So the first being wind, second solar, and then third, using the atmospheric CO2, using a methanation reaction to run a turbine.
Okay, so the overview. Again, we want to sustain a colony, and it needs to be about 160 people. We figured that was a good number to, set up camp there and achieve a bunch of operations. And again, this controller is going to have to control this electrical turbine that runs on methane. Our manipulated variable is going to be the percent that this valve that feeds methane into the system is open.
And so we modeled our three different power sources. So our first is our turbine, and using the literature, we found that about 10 minutes is a good dead time. And using thermodynamics, we found that 330 kilowatts per flow rate of methane. Second, we found out that we needed about 60 windmills, and that was given the fact that the atmospheric density on Mars is about 0.6% of Earth. And then lastly, for solar, using the literature value of about 19% efficiency, and we found that we needed about 100,000 meters squared, which is about 20 football fields of solar panels.
Okay, so there's going to be disturbances, right? There's issues. The first thing is dust storms. Mars actually sometimes has global dust storms that cover the entire atmosphere of the planet at one time. Obviously, this will decrease solar efficiency. We took that into account in our model. Also, Mars has an eccentric orbit compared to Earth's. It spends a lot of its time further away from the sun during the winter, and this drastically changes the solar flux. So we had to plan for that and model it after the winter to make sure we had enough methane then. Also, for any colony, you're going to want to be able to return to Earth. So we needed to model it and optimize it for a little bit of excess methane production that could be liquefied and then used to fuel our return rockets. Also, a colony suffers or has the same demand fluctuations that any normal power system on Earth would also have.
With all of these disturbances, we needed to make sure that we tuned our controllers very well. So we built a cascade controller to ensure that we had no blackouts. That was our goal, no blackouts at all. So the slave controller was the valve control. The output is the flow rate of methane into the tank or into the turbine. Manipulated variable is opening and closing. So we did a doublet test to find how it responded. And we tuned it using ITEA, IMC, and then tuning it from there. And then the master control from the Cascade was the turbine control. And for that, we really only cared about the rise time because that's how much more the rest of the system is going to have to work, i.e. more chance for blackout. So we got it down to 5 minutes with our ideal tuning parameters.
Okay, so after that, one of the things we had in the model you can see here was the methane production. So we used the Sabatier reaction that Colin touched on a little bit. And so that methane is produced whenever you have excess renewable energy sources. And so if we go on, so one of the problems we noticed here is, if you'll see right here, is that our turbine didn't respond quite fast enough as our power colony demand might want us to. And so in order to figure out a way to get instant reaction to the system, we decided to design a battery. And so you can see down here, there's our battery system. And so this battery charges, it's the first priority of the system when there's excess renewable energy, and it charges itself so that it can be used at night. And so here is our system. We modeled 1 day of each season, and if you look real close, you can see how well our system is responding to the disturbances. And so you'll see here is the colony demand is this orange line, and the blue line is the total energy being produced. So you can see that it only ever goes above but never falls below. And the reason for that is whenever you have a fluctuation in wind, you'll see that the battery, for example, right here, the battery turns on and then it starts to turn down as the turbine adjusts, and so you get you don't have any brownouts, no blackouts. And so we were able to create a really good system without any blackouts, and we feel like it could go tomorrow. So, any questions?